The chi-square distribution arises when you randomly draw n numbers from a standard normal distribution, square them, and add them up. This variable will follow a chi-square distribution with n degrees of freedom. Like the t-distribution, the chi-square distribution is determined by this one parameter, the degrees of freedom. In this code down here, I'm drawing a sample of 10 standard normal random variables, squaring them, and summing them up. I do that 10,000 times, and the distribution I get fits a chi-square curve with 10 degrees of freedom. We covered two chi-square tests in this class. This one is called the goodness of fit test. We perform this test when we want to see if our data follows some discrete distribution. In a discrete distribution, the data fall into categories. We gather data and see what the counts are for each category and then compare them to the expected counts. We use the difference between what we observed and what we expected to compute this statistic. And it follows a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. For example, say I have a die, and I want to know if it's fair. If I roll it 120 times, my expected counts would be 20 for each category. If the observed counts are very different from this, that would cause me to conclude that the die is not fair. This chi-square statistic is measuring the difference between what you observe and what you expect. The null hypothesis for the goodness of fit test is that the population you're sampling from has some specified distribution. The alternative hypothesis is that the population doesn't have that distribution. The chi-square statistic is always positive, and because it measures the difference between what you observe and what you expect, you reject the null hypothesis when the chi-square statistic is large. This is always a one-sided test where your p-value is calculated from the right tail, the greater than direction. The two assumptions we need for this test are independence. All observations are independent of each other. And we also want the expected count in each cell to be at least 5. It's okay if the observed count is less than 5, but the expected count needs to be at least 5. And this is just a general rule of thumb. It's not like the test is bad when some of the expected counts are below 5, but magically becomes good as soon as they get to 5. But this is one thing you should check. Sometimes, if your expected counts are too low, you can group the categories. Like, let's say I have a situation like this. My expected counts are because these last two categories have fewer than 5 expected counts in them, I can group the last 3 together like this. Now the expected counts are at least 5 for each group. Here's an example. I got this breakdown of blood types from somewhere. And we have this sample of 125 people whose blood type breaks down like this. Our goal is to see if the blood types for the US population break down like this. We'll perform a chi-square goodness of fit test at the 0.05 significance level. If the p-value is less than 0.05, we'll reject. If not, we'll fail to reject. To get the expected counts, we multiply each of these percentages by 125. And that's what I've done here. It's okay that some are not whole numbers. We do have an expected count of at least 5 for every group. We can proceed with the test. Here's the calculation of the chi-square statistic. It's observed minus expected squared divided by expected for each group. Then you add them all up. This gives you a statistic that follows a chi-square distribution with 3 degrees of freedom. The degrees of freedom for this test are the number of groups minus 1. In R, P Chisk will give you the area behind the statistic under a chi-square curve. Because we always look in the greater than direction, we use 1 minus P Chisk. We could also set lower tail equals false. And as usual, this version is more accurate when the area is very small, but it really doesn't matter which of these you use. In this case, our statistic was 3.277, and it shows up here on a chi-square 3 curve. The area above this is our p-value. If the null hypothesis is true, the probability that we would get a chi-square statistic at least as great as 3.277 is 0.3508. That's not very unlikely. It's above 0.05, so we fail to reject the null hypothesis. We cannot conclude that the U.S. population distribution of blood types is different from what we were given. Remember, we never accept a null hypothesis, we just fail to reject it. R has a Chisk test function that will perform the test for you. It's looking for X and P. X is the observed counts you saw. P is the probabilities for each group under the null hypothesis.